Okay, hello everyone. It's my pleasure to give a presentation here about the crop monitoring and production estimation with remote sensing. Okay, Professor Chen have already introduced the development and opportunities and the challenges of the agricultural remote sensing. Now, in my part, I want to introduce some related details, technical details for the agricultural remote sensing. So, okay. First of all, let's think about a question. How does farmers or ranchers observe their fields? Generally, most of them use their eyes to observe the overall appearance of the crop plants, such as the color of the leaves, to determine the current crop growth condition, and then they will or implement the relevant management measures based on their experiments, such as to irrigation and fertilization, and the remote sensing technique provide another way to evaluate the crop growth condition. It can not only observe more wavebands, which is not limited to the visible light range that only can see by our own eyes, but also provide the quantitative monitoring of the crop growth standards. Okay, today we mainly focused on the three aspects of the agriculture monitoring. First one is for the crop growth process and its status evaluation with remote sensing. Okay. As we mentioned above, farmers evaluate their crops through the height of the canopy coverage that they see and compared with the other years of the past years, and also they can see the leaf colors and the growth speeds. But all of these are mainly based on the farmer's own feelings. But for the scientists, they observe the status of crop growing with the measuring tools, and they considered more biophysical parameters. And the remote sensing can provide these two to observe the crop growing parameters, and which can help the scientists understand the crop growing standards, such as the canopy reflectance and the vegetation indicators, and which is found to have the good relationship with the LAI or the F cover or LNC and such such parameters. Okay. Okay, the indicator provided by the remote sensing to assess the crop growth standards usually involved with NDVI, EVI, or SVI, LAI, and so on. And usually the crop evaluation with remote sensing considered as the two aspects. First is to evaluate the situation of crop plants through the indicators, and then to consider the process of the vegetative and the reproductive period through the profile of the indicators. Okay, normally in most of the time, the higher NDVI always means the stronger a crop, and vice versa. Also, this principle was always used to evaluate the situation of the crop growth. And here we give an image and geo-tagged photos at different plots. The more obvious red in this image, and the higher NEVI and the EVI values, and that it means the health situation of the wheat. And the crop situation evaluation through the VI profile analysis is just because the crops always go through a process of NEVI value rise and a process of the NEVI VI value drop. So the rise of the VI means the crop grows from the seeding to flowering, and the drop of VI means the crop mature. And since the higher VI means the higher VI means good crop growth situation, and the higher speed of the rise of VI. Oh, okay, this part I think like here the rise of VI profile means better development of the crops, and the slower the slow drop of VI profile means satisfied crop yield process, like this part. That's after the peak of the VI values. So and this principle always used to analyze the development status of crops and always linked to the crop yield estimation. Okay, let's consider how to give the crop growth standards evaluation use the remote sensing data. Okay, we use many multiple remote sensing data sources such as the MODIS and Signal2, and the indicator that we used mainly with the NEVI or EVI or that. We just select one of them to which is suitable for the region that you are interested. Okay, firstly, let's see the process of the growth, the process of the crop growth standard evaluation at a fixed frequency, such as we want to assess the crop growth standards every week or every 10 days or every month. Firstly, we have to calculate the NEVI or EVI or other VI or parameters at the fixed frequency, such as at a week or at every 10 days or other periods. And then the indicators were compared with standard reference data to get a differential image. For the standard reference data, it can be the crop standards last year or the average level for the past 5 years is up to your requirement. Okay, the differential image was then can be classified into 6 levels or 5 levels, whatever, which means that the excellent, means that the crop growth status is excellent or good, fair or poor or worse level. And secondly, let's see the process of the crop growth standards evaluation from the growth process. First of all, the certain VI should be selected for depict the crop growth, such as EVI or NEVI that we mentioned above, and then the crop growth profile based on this selected VI should be reconstructed. And finally, is analysis such as the crop rhythm analysis from the comparison of the upgrowth point to the trend of the NEVI profile, and the crop growth speed analysis from the decision of the upgrowth speed of the profile. Okay, here is an example of the crop growing standards evaluation. Okay, here the green crops in the flooded region was slightly influenced, while the good growing status happened in other area of China. In this example, in 1998. Okay, the next one is an example for the crop growing standard evaluation in USA in 2011. And the crop growth situation in the US this year was not very optimistic, and the overall situation is obviously not so good as 2010. Okay, here is an example of the crop growing standard evaluation in China in 2011. Okay, we can see the crop growth profile in China. The left one is for the dryland crops, and the right one is for the paddy field. Okay, next we will introduce about the crop identification and accurate estimation with remote sensing. Okay, so the traditional theoretical basis of the crop planting area estimation is mainly sampling and reasoning, and the statistical sampling survey theory was extracted in 1957. So in terms of sampling, it has also experienced development process from single random sampling to the cluster sampling. In terms of the spatial sampling, the main representatives are the tessellated plane sampling and the continually plane sampling. And there are also some advantage and disadvantage to estimate crop acreage based on the static sampling series. The disadvantage include no mapping, but only estimation for a region, and the workload is relatively large, and the cost is relatively high. And the advantage is that the estimation accuracy is controllable. That is, if you want to further improve the estimation accuracy, and you only need to further increase the sampling population. Okay, so with the development of remote sensing technology and the use of remote sensing for crop identification and the accurate estimation has become more and more important, and its application have become more and more extensive. Okay, the basis of the crop accurate estimation with the remote sensing is to identify the crop type using remote sensing images. And the basis of crop identification with remote sensing is that different crops in the same period have different reflectance features. Okay, at the different wavelengths. So, for example, the growing cycle of corn and the soybean is exactly the same, but the reflectance of corn and soybean at different wavelengths is totally different in the same periods, just like this picture. Okay. It is same for the winter wheat and the seed rape. So growth process of crops is a slow and dynamic process, and there are some difference in the growth process of different crops, and the growth process of crops can be depicted with time series remote sensing data. The conventional method is to construct the time series vegetation index data set to express the the growth process of the crop, and then use the differences in the growth process to complete the identity of crop type. For example, okay, here the growth profile of winter wheat and the river basin in China, okay, including the process in the visible band and near infrared band and the NEVI and the EVI. And from this picture, we can see that each crop shows some feature different compared with the other crop during its growing cycle. Okay, for another example, this time series NEVI is the most commonly used vegetation index to describe the growth process of planting. We can see the difference in the growth cycle of several crops such as corn, alfalfa, soybean, and sunflower. This temporal feature is one of the important characteristics to identify the different crops. In addition to the features that we mentioned above, such as the original spectral features and the VI features and the temporal features, the text features is another important feature type for the crop identification. Since different crops have the different canopy morphology and different planting and with the different planting method of the management. Okay, this will show different texture features on the image. So in an actual planting scene, many crops may have similar spectral characteristics. At this time, it's very effective to consider the difference in the texture features. The texture feature has relatively little correlation with the factors such as the crop growth cycle, the spectrum, and the environment. The use of the texture feature is beneficial to improve the accuracy of the remote sensing, accuracy of crop identification with remote sensing. So the texture feature extraction method used commonly are as follow for the grade level co-occurrence metrics, just short as the GLCM, or the Gabor transform, LBP, and the wavelength transform, and so on. Okay, there are many commonly used classification models. First is for the box model, also called the parallel algorithm, which use the lines to divide the feature space into different subregions, and the different subregions represent different categories or different crop types. The other one is for the decision tree model. Here, in this model, the node is continuously divided into two parts until each node cannot be further divided. At this time, a classification binary tree is formed in which each node represents one type. And also there is the distance-based model. Firstly, in this model, first define the centers of the different crop types, and then compare the distance from other pixel to the center of each crop types, and then to determine the crop types of the pixel based on the distance. Okay. the support vector machine models. The core idea of this method is to find the optimal hyperplane between the different crop types in the feature space for the neural network model. Which is a hotspot of the current research and a method with many usage scenarios. And the final one is for the spectral Andro model, which is to classify the crop type according to the Andro in the feature space. Okay, this is the introduction of the classifiers. Okay, let's give an overview of the basic process of the identification and accurate estimation with remote sensing. Firstly, we need to select the images and collect the image features such as the spectral features and all the textual features. Secondly, we need to clean the features to generate a prediction model or a classifier. And use the model to generate the crop distribution map. At last, we built the models to estimate the crop acreage based on the crop distribution map. Briefly, the image classification is a process of assigning the pixels to the classes. The basic process of classification is to compare the similarity between the feature vector of each pixel and the feature vector of the predefined crop type. After the classification is completed, the internal difference of each crop type is the smallest, and the difference between different crop types is the largest. This picture shows the basic process of the classification. Here is an example of the early rise, middle rise, and the late rise distribution maps of Hunan province in 2012 in China. And here is an example of the rice crop acreage of Hunan province in 2012. And the result was used by the government to account the green subsidies. Okay, so the last one we will introduce about the crop yield monitoring with remote sensing. Generally, the crop growing process can be divided into the vegetative process and the reproductive process. Okay, the former process, so the vegetative process means that the plant grows from a seed to become a well-grown crop plants, aim to develop a healthy plant. And the reproductive process is for the yield oriented. From the flowering stage to the green fielding stage. Okay, the factors are related to the crop yield involved the climate factors or the fertilizers. So for the crop yield estimation, these factors should be considered in the modeling. Usually, there are three elements of the crop yield that must be measured. That is the spike number, the green number of per year, and the green weight. Then the yield, the crop yield, can be the product of the three elements. It's worth noting that the spiking number is always related to the growing status during the earlier stage of the growing stage. The green number per year is related to the growing centers of the middle period of the crop, and the green weight is related to the growing centers of the in the green fielding stage in the late period of the crop. Traditionally, the crop yield can be estimated with field sampling, and the yield was measured in the field plots and used to estimate the field level or the administrative level. In addition, crop yield was also estimated or predicted using the agrometeorological model. Lately, the crop growth simulation models were developed, which are more perfect models, such as the Wolfort, Epic, or Cirrus, and these models are also can used in the crop yield modeling. Okay, for the operational crop yield modeling, usually based on the most of them are based on the agrometeorological factors, and the yield. In this model, the crop yield can be divided into two separated parts. One is called the trend yield, means the average level of the crop yield due to the development of the science of the practice the measurement. Another is assumed as affected by the weather fluctuation. So the trend yield usually simulated use the smooth algorithm such as logarithmic model, and the weather related yield can be simulated use the multivariate regression or the ANN or SVM model. Okay, the remote sensing image reflected the status of the crop growth. So the remote sensing indicators such as the LAI, VI, or event transpiration usually were involved in the crop yield estimation models. These remote sensing indicators were mainly used to collect the crop developing parameters to depict the crop growth, to estimate the accumulation of the photosynthesis and the partitioning ratio. And the remote sensing yield indicator indicators can also be integrated into the crop growth simulation model together with the meteorological data that the Professor Chen has already introduced in his presentation. Okay, here is a framework of to estimate crop yield use a hybrid model. This model comprehensively utilized the estimation result of the multiple models to ensure the accuracy of the final crop yield estimation results. Most of them are a combination of the agrometeorological model and the remote sensing parameter model. Similar to the agrometeorological model, for the in this model, in this hybrid model, for the trend yield estimation, smooth algorithm are used, but for the fluctuation yield simulation, remote sensing parameters are also involved in addition to the meteorological parameters. Here's another framework to estimate crop yield with above ground biomass estimation and the harvest indexed estimation. The above ground biomass can be estimated using the remote sensing parameters and the meteorological conditions through various models such as the radiation use efficiency, based models, just like the Kata model or the CFIX model. The Harvard index is the ratio of the total cumulative biomass transfer into the green. It can be seen as a function of the meteorological condition during the reproductive period of the crop season, or a function of the crop profile during the reproductive period. Okay, the crop yield can also be estimated through the remote sensing simulation with the crop growth model, and that is very complex work, but can get a higher accuracy. You can use that in the plot level or the field level crop yield estimation, but for a large area, it's not very suitable. For in this framework, the IOAI and evaporation were usually considered as a simulation variable. Okay, here is the example of the winter wheat yield estimation in Henan and Shandong province of China from 2005 to 2008, based on the biomass and harvest index framework. And here is the corn yield estimation in Henan and Shandong province of China from 2005 to 2008, based on the biomass and harvest framework. Well, all of this above is a general introduction of the main content and some basic principle of the agriculture monitoring with remote sensing. Next, we will give some demonstration on the specific operation of the crop classification and the yield estimation with remote sensing. Okay, first one is for the crop classification. 是不得结束一下，结束了，然后把视频打开是吧？是这吗？哎，不对，哦，这个，下边这还配色啊，对，然后打开之后，然后还要把那个图像切换一下，就不能让它部分，让你全部。哦，对。你怎么把它暂停一下？那个操作手册。Okay. This is the Henan practice for the crop classification with remote sensing, and in this video we will use the NV to show how to implement the crop classification with the remote sensing data, and we have already prepared the experiment data. But if you are interested, you can download this data after this presentation and to operate these steps according to the protocol. Okay, that's it. Okay, first of all, we should open the data in NV, and in the pop-up dialogs. Okay, we will select the image data, and then we go to set the image display effect, and here we use a false color display. The red is set to bound 4, and green is set to bound 3, and blue is set to bound 2. Okay, here is for the ROI selected. Here we will create the ROI for the rice, and you can create a new ROI, and then yeah, 态度，突然忘了到哪儿了。Okay. Okay, for the this step is for the other. Okay, I forgot to introduce that. For these experiments, there are only two types in our the classification systems: the rice and the others. We only to classify the rice and others. If you use the real crop classification, and maybe you there are 3 or 5 crop types, and then you should create all of these ROIs for the training data. Okay, when we finish the ROI selection, then we should save this as training samples. And for the classification methods, here we select the maximum likelihood classification, and in the to avoid the okay, we should wait for a moment, because okay. To avoid the effect of no data on the classification result, we need to build the mask data. So this step is to build the mask data, and we don't wait for the output. I think we can go fast. Like this. Okay. Okay. When we finish to get the mask data, here I have something to in this part. No, just here. There's something we should notice, that here we select in the MLC method, we should complete the parameter setting first. If the single value is selected here, if the single value is selected, we should have to enter a value between 0 to 1 in the probability threshold text box. If the likelihood is less than this threshold, we will not be classified into this class. Okay, so in this experiment, we selected no. Okay, this for the output file. Okay, it's running, so we can go fast of this step. Okay. Okay, here we get the output of the classification results. We can see that the rice and the other crops in different colors, and the rice is in I think it's red, and the other crops is in the color of green, I think. And you can also to edit the colors of the crop types, that whatever you like. And you can also edit the name of the crop types. And after the crop classification results that we have acquired, and then we have to do the okay. In this picture, in this picture, we can see that the rice is showing the green color, and the others are not highlighted. Okay. Okay. After the classification, the final step is to do the accuracy analysis. Here, we should prepare the test data set first. But for the test data set, you can also, there are two ways. The first way, you can also to select ROI, just like the training data set, but also you can get the, but it's better to get the test data set from based on the, I think based on the field survey. With the field observation is much better. Okay, we have already prepared the test data set, and then you can see that just like here. Okay. For the accuracy assessment, here we use the computer metrics to evaluate the classification result. Okay, the software will automatically match the crop types. Okay, according to the classification code. Yeah, if it's not correct, we can change it manually. Okay, here is the confusion matrix for the classification result. Okay, we can save that as command. Okay, so if the accuracy assessment is satisfied, So we should to move to the next step because based on the crop classification result, we also need to compute the crop acreage in this region. So we should use the statistics function of this software, not like this. Okay, here we can statistic how many pixels of rice in this classification result, and then we can get the crop plant, the rice plant area in this region. Okay, and present. Okay, we can also click that. Okay, that shows the acreage and the ratio of these two kind of crops. Okay, that's all for the crop classification with remote sensing. Okay, we will go to the other one, the crop yield modeling with remote sensing. 直接开就行了，是吧？我再开另一个，开另一个啊，这儿。现在是这个吗？ Okay, this is for the crop yield estimation with remote sensing. Here we use signal 2 data for the test data, but we only use 4 bounds of the data. We will not use all of these bounds. We use bound 1, bound 4, and bound 7, and bound 8 to create the test data, test image for the crop yield estimation with remote sensing. And here we can open this image. Okay, data.tif. As open, we can see that, and based on this image, we can calculate the several VIs. And also, if you have other models, you can also calculate such other parameters such as REI or environment transformation. Here we use the bandmass to directly to calculate the NDVI, and we also can calculate the REI, TVI, whatever, if there are enough bounds, and we can. To finish the calculation, and then we use this equation to calculate the crop biomass. The NDVI. Okay. So here we should to set the variables to the corresponding rank bound. For example, for the B4 is for the bound 4, B3 is for the bound 3. Then we can go to the NDVI file. Okay, we go fast. Oh, okay, that's this. when we get the parameters that we want, here we only use the NUVI for example, and then we should have the sampling data for the crop yield, and then we can create the crop yield, create the relationship between the crop yield and the NUVI or other parameters. Here we use the NV to extract the corresponding NUVI value of the sampling point that we have the crop yield value. Okay, this is show the crop yield value for the sampling data, done like this, and then we should to extract the NUVI value or the other parameter value one by one. Okay, there are the tools for the, we use the tools vector to ROI to get this one. Okay, you can see this point. And then we can export the data. We use the summing point to get the NUVI value in the image, and then we can do the analysis with the crop yield model that we get from the observation. Okay, this is the output. We can open that in the Excel. Okay, I'm sorry, I only have the Chinese word. Maybe you can use the English word. But in the project, we have already changed to update for the English version. Okay. Okay, in this step, we create the carbon yield estimation model, and then we use the model to the whole image and get the area, get the carbon yield estimation in the whole area. But in this process of training the model, and if you want to choose a complex model, such as random forest, regression, and SVM, or even the deep learning method, if you have enough samples, and then it is recommended that to use the software such as MATLAB or the IDL or the Python for the data analysis. But in this demo, we only use show some easier way to get an easier model. Okay, here we get this linear model, and then we can use this model to our whole image. Then we can get the crop yield distribution map. Okay, here you can see that this is our model of that. And then we use NV in the for the bandmass to apply this model in the whole image to get the crop yield distribution map. Okay, this is for the okay. is a curve yield model. We use that in the whole image. The bound we should select is NEVI because the parameters of this model is that we use is simply NEVI. Okay, then this is for the output of the. Okay, we can see the value. It's about too fast. It's about 408. I think it's 408, 480 kilogram per mu. Is a Chinese area unit. And then we can create the crop yield distribution map with the ME. But I think if you want to get a picture of the output, it's recommended to use the ArcMap, and it's much more friendly. For the NV software, the advantage of this software is the raster calculation. It's not for the map creation, and but it also can output a picture of that. So here is added the density slice range in this. Okay. Okay, we can edit the range by our requirement. Okay, and then apply. Then we can get the picture, and then we can add some elements for the quick map. Okay, then get a beautiful thematic map. And we can also add the main title and the skill bar, or the north arrow, or the grid line. If you need that, you can okay. Yeah, that's the color of the map. And then you can ideate the element of the map. The quick map. Okay, you can see that okay, here the quick map parameters ideation, such as the main title and the skill bar here, the grid line, or the north arrow, and then we can see the whole picture here. It's not so friendly for the not so friendly as the ArcMap. I think you want to export a map, I think you can calculate the crop yield in the NV software, and then you can export the map with ArcMap. Okay. Here it's for the legend. Go faster for the legend edition. Yeah. Font size. And we can get the legend. Then we can output this. Okay, this is finally the output of the crop yield distribution map that estimated by this experiment. Show that, okay, we can open that. And that's like, okay, this is output. So the final output of the crop yield map. It's not very so clear, but for the legend, it's like from the output is main in the I think it's higher. The crop yield is higher than most of them is higher than the 400 kilometers per move in. Okay. Okay, that's all for all of the content of today's presentation. And if you have any questions in the future, you can send me an email, and I'm very happy to discuss with you. And I think the experiment data will be shared with you after this presentation by Dr. Wang Jing, I think. Okay. That's all. Thank you.
Okay, thank you very much to Dr. Zheng.
Thank you very much, Professor, for your kind information to us.
And there's some questions from our training. The first one is, what is the software? It's NV.
It's NV. You just can Google it.
It's NV. You can use NV trial version, or you can buy it in your institution. Okay, Ms. Evan. And the next question is, when Dr. Do operate, the question is, can this method of remote sensing be used to determine irrigation schedule under crop water requirement?
Yes, for example, if you want to use in the determination of the irrigation schedule and the crop water requirement, I think you would estimate the preparation of the crop by I think you can search for the Serbo model or the Cibos model for the crop environment preparation estimation with remote sensing. And then if you can get the actual environment preparation, and then you can use this information to guide you how to implement the irrigation and to assessment the crop water requirement in the certain